All right, our second video from chapter 5 is where we actually get into the reactivity of alkenes in the case of chapter 5, but this is where we set the framework for the rest of organic chemistry, this and next semester. Because if you remember from chapter 3, when we first introduced the idea of a functional group, and we had 4 of them we were working with, and we had alcohols, amines, carboxylic acids, and ethers. Those, as we said when they were first introduced, control how organic compounds react. And we got a word back then that was in our vocab, homologs, or a homologous series. It doesn't matter if I have, say, 10 carbons and 3 carbons. If they both have an OH, they're both alcohols and they react the same. So the whole strategy for organic overall, we don't want to memorize how every individual compound reacts. It would be impossible. There's something, I think, 23 million organic compounds that have been categorized in the world. So imagine trying to memorize every reaction for every compound. It's just not something a human could do. So we look at functional groups specifically because compounds that have the same functional group react similarly to one another. And so the first functional group we're looking at in chapter 5 is alkenes. But basically every chapter in organic, save a few, we pick a functional group and see how that thing reacts. And in general, excuse me, our functional group families can go into 4 groups that, if we're painting with a pretty broad brush, react similarly to one another. Okay. And this is a really key figure. It's in chapter 5 in your textbook, and you're going to continue to see it throughout this semester and next semester if you're continuing to organic 2, because these are the 4 groups that we target in organic chemistry. Chapter 5 is where we begin in group 1. Okay. Specifically, chapter 5 and 6 look at alkenes. Chapter 7, that triple bond in alkynes. And this is called a diene right here, 2 double bonds. That was in the first video as well. A diene, we see how those react, any special classifications in chapter 8. And that takes us through most of organic 1, seeing how group 1 reacts. We have a little bit of an introduction to group 4 over here in chapter 8 as well. And then organic 2 is all about seeing how group 2 and 3 react. That's pretty much the strategy from here on out. As I mentioned, we pick a functional group, figure out how that family reacts similarly to one another, which is a nice thing going forward. The reactions we learn starting today in chapter 5, we'll use again in chapter 6, and they also happen to things in chapter 7. Something that will react with a triple bond or a double bond, can also react with a triple bond. It just happens twice because there's 2 pi bonds in a triple bond. So let's start with group 1 and our alkenes from chapter 5. Right? Look at this. Double bond here in just ethene, the simplest double bond we could get. And a double bond down here in cholesterol. Both of those, if you expose them to hydrobromic acid and HBr, you end up adding the H and the Br on opposite sides of the bond. See it happening here. I've added the H and the Br, the H and the Br. Even though those molecules are incredibly different from one another, right? The fact that they both have that double bond there makes them react the same, regardless of their size. So that's why they're in the same family, because they have the same functional group in this case, and they're related to other functional groups. So you can think about the alkene, right, as being one member of the family, and then it has its cousin, the alkyne. And then I've already said all of this verbally, right, looking at alkenes first, functional groups the rest of the semester. But moving forward, we get some new terminology. So I strongly recommend you write these words down and know their definition. If you want to get ahead of the game, we're going to use them so much, you're going to not have any choice but to learn their name. But it's going to help you understand these things drastically if you know the words ahead of time. And the whole goal Right. As I said, it would be impossible to memorize reactions for every molecule. But as you will quickly find out, it's really almost impossible to memorize the reactions for every functional group because there's so many and there are things that are being discovered every day still. So the goal isn't just to memorize a reaction, right, but rather to understand why the reaction's occurring, right? You learn addition. You don't just memorize the fact that 2 + 2 is 4. You want to try and do the same strategy here, right? Understanding the principles of reactivity so you can predict what happens in any reaction you're targeted with. Okay? And if you really boil it down, it's kind of a strange abstract thing in some places, especially when we get into the world of organometallics in chapter 11. Right? But organic, if you boil it down, is all about interactions between things that are electron rich and electron poor, or electron deficient on this slide. That's the force that makes reactions happen. And if you think about it, we already did this to an extent in chapter 2 when we learned about acid-base interactions. That was kind of freaky when we first saw it, right? Because we took the Gen Chem definition of acids and bases and kind of turned it on its head and said, oh, in Gen Chem, we said there were only 7 strong acids. Psych, right now there's an unlimited amount depending on their pKa. But the reason that these things acted as acids or bases is because of their electrons, right? If I had a strong or a conjugate base that was nice and stable, then that made something acidic. Something would act as a base if it had a lot of electron density. So we're using that same idea, electron rich and electron poor, to drive principles of reactivity. But not everything is a straight up acid-base reaction. So I need a little bit broader of a term. And those terms are electrophiles and nucleophiles. Those are the terms that have written down, underlined, starred, right, highlighted, electrophiles and nucleophiles. We'll use those words in every chapter from here on out. And electrophiles can exist in a couple of different manners. You see them listed down at the bottom here. A positive charge, a partial positive charge, or an incomplete octet. And you might want to add a note down there. Right? We see that incomplete octet with Lewis acids pretty frequently. Yeah. So if I take these two on the left, those are super easy to identify as electrophiles. Right? There's a positive charge right on it. That's like the blinking red light. It's like, this is clearly an electrophile, anything that has a pure charge. Okay? But that's not the only one. So they're the easiest, but they're not the only ones. Jumping over to HBr over here, this is an electrophile, not the whole thing, right? But the hydrogen part of HBr. Because of that difference in electronegativity, right? Bromine being the more electronegative, it's pulling the electron density towards it. It's leaving a large partial positive on hydrogen. So that's allowing it to act as an electrophile. Okay. And then boron over here, BH3, the boron has an incomplete octet. If you were to draw the Lewis structure out for that, it's boron with 3 sigma bonds going to 3 hydrogens, right? So it only has 6 electrons around the center atom. Remember the octet rule is 8. So 6 of 8 electrons, incomplete octet, also allows it to act as an electrophile. We'll see that a lot in organic too. Right now, we're focusing on these ones with full partial positives or partial positives. I said full partial positive. That doesn't make any sense. With a whole positive or a partial positive. So that's an electrophile. Electrophiles react with nucleophiles, which is the opposite. Okay, nucleophiles have either a whole negative charge, like I see on hydroxide or chloride over here. Okay, those are, again, are the easiest ones. Notice what's not listed here. Partial positive will be an electrophile. We don't use nucleophiles that are partial negatives. Okay, so it's a whole negative charge. A lone pair, like I see on water or on methylamine over here. Right, you can see that lone pair right there, or a pi bond. Okay. So now that might be triggering something in your brain. Okay, chapter 5 is about alkenes. We just mentioned the fact that alkenes have a pi bond. Those alkenes are nucleophiles. That's what we're going to be working with in this chapter. Chapter 5, alkenes are nucleophiles. Let's expose them in chapter 6 to a variety of electrophiles and see what happens. But at the end of the day, your electrophiles are the things that are electron deficient. Your nucleophiles on this slide are the things that are electron rich. They have a pair of electrons that they can share, and they share that pair of electrons with the electron poor nucleophile. In each situation here, right, I've got a lone pair of electrons that can be shared. The pi bond is also what's going to break to be shared in a reaction. That's why we talked about where those electrons are above and below the plane. Right, so the golden rule moving forward, electron deficient species, those are the electrophiles, partial positives, are attracted to electron rich species. Those are the nucleophiles. And that also still holds. If you go back and look at an acid-base reaction from chapter 2, you can assign electrophiles and nucleophiles using those rules. Right? It's not a violation of what we've learned in the past, it's just an expansion. Okay? And that allows us to understand the patterns of reactivity. Electrophiles react with nucleophiles. So that's general. What are we looking at specifically for alkenes? Well, as I just mentioned, the alkene has the pi bond. Yep. It's got the double bond with the sigma bond directly between the two atoms. Okay? It's called the internuclear axis, if you remember that from Gen Chem. That sigma bond is not what's reacting. It's the pi bond. Right? Pi bonds are weaker than sigma bonds. It's the electron density that's above and below the internuclear axis. It has a lot of electron density there, making it electron rich and allowing it to act as a nucleophile. That nucleophile, the alkene, reacts with an electrophile and breaks the pi bond. Okay? When that pi bond breaks, I form a bond to one of the two carbons that was involved in the pi bond, right? Because that pi bond was going between two carbons. One of them forms a new bond, but one of them lost its pi bond and didn't get a new bond. Okay? So it only has 3 bonds going to it, meaning we temporarily have a carbocation. Remember, that means a positively charged carbon. And then in the second step of reactions of alkenes, that carbocation, which has a positive charge, meaning it's an electrophile, picks up a nucleophile in solution to form a new bond. So those two slides, 31 and 32 here, give you the general description of a reaction of an alkene. Right? The back half of chapter 5 and chapter 6 are all the different variations of those reactions we can see. Right? And as I alluded to at the beginning, this is the exciting day. Right? This is your first organic reaction. An alkene plus HBr. Okay. In chapter 6, we'll expand this to hydrogen halides, but at this stage in the game, we're just thinking about HBr. Okay. So what happens here? Let's think about everything we just learned, right? Alkenes have a pi bond. Pi bonds are nucleophiles. HBr here, hydrogen has a delta positive. That partial positive allows it to act as an electrophile. So I have the 2 pieces I need. Right? If you have 2 nucleophiles or you have 2 electrophiles in solution, they're not going to react with each other. Right? But here I have a nucleophile and an electrophile. That nucleophile reacts with the electrophile. This pi bond, notice it disappears over here. And I picked up my electrophile. So I have a new bond to hydrogen. That left behind the carbocation. Now that's a positive charge. So now it's an electrophile. But what got left behind over here? Bromine. Bromide specifically, Br minus. So sure enough, now I have an electrophile and a nucleophile again in solution. So immediately that gets picked up and I form a new bond. Okay. I went from an alkene to forming an alkyl halide. So that's what's here on slide 33. Notice the double bond got an H and a Br. And if I jump back a couple of slides here, notice that that's the exact same thing that we saw. Oh, did I overshoot it? Yeah, I did. On slide 25 here, right? The double bond picks up an H and a Br. The double bond picks up an H and a Br. It added those two atoms, so this is called an addition reaction. I don't know if that's in this group of the slides, but it's coming later on, right? It added atoms, it's called an addition reaction. So you've seen in your rubrics for lab asking about a reaction mechanism. We just learned on slide 33 there what the products are, but the big challenge in organic is showing how things actually get formed. And that process is known as the mechanism, right? A step-by-step description of the process where I take my reactants and convert them into products. And this is where we use those curved arrows that were first introduced back in chapter 2. I don't know if you guys recall in class back in chapter 2, I was like, hey, look out for these, pay attention to the curved arrow notation because this is going to come back. Well, as promised, here it is, and we're going to use it extensively from here on out. Okay. And these curved arrows shown here in red, right, they're different from the reaction arrow that's there in the middle. The reaction arrow just separates out the reactants and the products. These curved arrows are all about tracking the electrons, showing where they start and where they go. And as those electrons are moving around, it also helps us track when bonds are formed and when bonds are broken. Yeah. So now we can think about it a different way, right? If I'm showing the origin of this arrow, back in chapter 2, I would have told you that arrows originate at electron density. Now you can think about electrons as moving from nucleophile to electrophile, which is happening here. My arrow is going from my nucleophile with the pi bond to my delta positive hydrogen, the electrophile. That's different from this one. This is showing that that bond breaks and the electrons are picked up by bromide. So a couple of things to note here, if you're jotting down notes as we go. In addition to what I just mentioned, going from nucleophile to electrophile, the tail of your arrow has to originate at electrons. So it's either always starting at a lone pair of electrons or at a bond. So notice here it's starting at a bond, starting at a bond. Right? So that's where it starts, and it always points toward an atom. So notice the arrow finishes at hydrogen, finishes at bromine. So start at electrons, finish at an atom. And notice that the arrows in this situation are two barbed, right, or two hooked. That means we're moving two electrons. When we get to chapter 12 in this course, we'll see about radical reactions, which only move one electron. But it is appropriate to always draw your arrows right now with two, as you would normally draw an arrow. We'll talk about one hooked arrows more in chapter 12, but if you see them in the meantime, that's what that means. So here, electrons started at the pi bond, went to hydrogen. Yep, that formed a new bond right here. But hydrogen's not going to stay bonded to two things, so at the same time, this bond to bromine broke, and the electrons went over to bromide. Notice that new lone pair right there. Then that formed the carbocation, which is now an electrophile with its positive charge, meaning that bromide comes over. All I have to show in step 2 is the bond forming. So that arrow going over, pointing to the partial charge, right? Arrow started at electrons, finished at an atom that's forming the new bond, and I'm in business. Okay, so again, this is a general guideline. These slides, 34 and 35, those were. That's going to help you get through chapter 6 with all those different reactions, because that first reaction follows the same recipe, for lack of a better word, as all the other ones we get for alkenes. Right? We added HBr. Right? The first step is an addition of an electrophile. So this is called an electrophilic addition reaction. The general scheme for everything, chapter 5 and chapter 6. But what I want to draw your attention to, what we finished the video on, because these curved arrows can be tricky. You don't want to mess them up. So just some general examples from other reactions. We're always showing every step, right? Every time electrons are moving, we're showing it with a curved arrow. And something I'll actually bring your attention to, simple little arrows like that, I'm not a huge fan of. Overemphasize the curve if you need to, right? Something funky like what's going on there, because that differentiates it from a reaction arrow. So always make sure you emphasize the curve, always start at electrons, always point toward an atom. Okay. So incorrect over here, right? Starting at electrons, not going to a bond or to an atom, right? Over here, what's wrong? Electrons pointing right at more electrons. So this is an example of two nucleophiles. Right? I wouldn't point electrons at more electrons. What about over here? Right? What's incorrect on the right-hand side? Take a minute, look at the left, look on the right. This is actually what I would point out as the most common mistake that I see when I'm grading tests. Right? The problem over here, why is this one not correct? Because it showed the arrow starting at an atom. You always want to start at electrons and point to atoms. How about on this one? Okay. I mean, this is just egregious. Hopefully this one you're looking at and immediately saying, man, who would ever do that? Right? It's just, okay, I want to get rid of these electrons, but I don't know where they go. Just draw an arrow off into space. Hopefully it never comes to that, because that's never going to be correct. Right? Law of conservation of mass. We're never going to violate that. Okay. What's going on down here? This is where it's key to be precise. Right? This is something that'll be on the take-home portion of the next exam, drawing stuff like this. Look at the subtle difference here. But the top is correct and the bottom is incorrect. This is almost like a game of Where's Waldo, right? This is correct because it starts at electron density in the pi bond. This carbon itself doesn't have any electron density, right? The bond has the electron densities, which is why I show the arrow starting there, not at carbon. So lots of subtle things to pay attention to, and your sapling is going to have a lot of practice for you to make progress on the curved arrows. Okay, so we finished with one idea, just reaction pathways, 2 slides here. Okay, these are something that should hopefully seem familiar from Gen Chem. Okay, reaction pathways or reaction coordinate diagrams. These were introduced for us in Chem 1560. Right, when reactants go to products, we can track energy changes. Okay. It can be an exergonic or an endergonic reaction, but no matter what, we always go through a transition state. Hopefully you remember that discussion from 1560. It doesn't matter if we net end up with more energy or less energy, we always proceed through this transition state. Okay. So we have my reactants, my products, right? But as we go there, right, it always happens through the transition state where bonds are partially formed and partially broken. And you might recall that's how catalysts work, right? They lower the energy of the transition state. They make this hill smaller. We'll build on these ideas in the 3rd video from chapter 5, but I just wanted you to finish with having that on your radar. We go reactants to products, or if we're in equilibrium, from products back to reactants, but it always occurs via the transition state, which is the highest point on the reaction coordinate diagram. So the key takeaways from this video, nucleophile and electrophile. I'm less concerned with memorizing this first reaction that we got because we're going to see it again in chapter 6, but laying the foundation is key. Notice how to identify an electrophile, how to identify a nucleophile, and how to correctly pair them together and draw the curved arrows to show reaction mechanisms. That's what you'll be doing extensively, so it's key to learn those fundamentals sooner rather than later.